Hey everybody, Mr. Kenyon here, and this is going to be the 68, 95, 99.7 rule. It's called the empirical rule in some statistics books. Let's first take care of this board problem here. The histogram here is it skewed to the right? Yeah, because it's got a long tail to the right. It's let's see, has an outlier. Sure looks like it has an outlier. Asymmetrical. Asymmetrical just means it's not symmetrical. So yeah, this is asymmetrical because it's skewed. Anything that's skewed is asymmetrical. So it has a mean that's less than 30. Well, that one I have to do a little calculation on here. Well, if this goes up to 60, between 0 and 10, and then 10 and 20, yeah, I would say it has a mean that's less than 30. So it's going to be all of the above right here. And I knew it was all of the above. As soon as I knew it was skewed to the right, asymmetrical, and it has an outlier. So I knew it was more than one answer, so it has to be all of the above. All right, so this is called the empirical rule, or the 68, 95, 99.7 rule. Oh my, here we go. In a normal distribution with mean mu and standard deviation sigma, that's going to be our new symbols now for mean. Okay, instead of x bar, we're going to use well, actually we'll use x bar again later. But for now, mean right now is mu and standard deviation is sigma. Okay, you'll get frustrated with the book going back and forth with the symbols, and just get used to it, you guys. 68% of the data falls within one standard deviation of the mean, okay, of the mean mu, okay? And I'll show you that in just a second. 95% of the data falls within two standard deviations of the mean, mu. And then 99.7% of the data falls within 3% of the standard deviations. I'm not 3%, 3 standard deviations. Did I say percent right there? This is 2 standard deviations. This is 3 standard deviations of the mean mu. Alright, so what the heck does that mean? Well, let's draw this picture right here. And yes, I'd like you to draw that. To go ahead and draw a normal bell-shaped curve. Here I have it on a bigger scale right here. You'll get used to this. You're going to be drawing a million of these, so get used to this, you guys. Just draw a normal bell-shaped curve going up. Okay, and then right in the center right here, put the number 0, and then go evenly spaced 1, 2, 3 to the right. Those are standard deviations. And then go 1, 2, 3 to the left. Okay, and the 3 to the left and the 3 to the right are almost out at the very tail end of that. It's way out there. So, okay, so here's the mean mu, 0 right there. One standard deviation to the right would be that way. One standard deviation to the left would be that way. So within one standard deviation of the mean mu, which in this case is 0, 68% of the data falls in there. Okay? If I went 2 to the left and then 2 to the right, that's 2 standard deviations. So within 2 standard deviations, 95% of the data falls within 2 standard deviations. And then likely within 3 standard deviations, almost the whole curve. Remember, the whole curve is 100% or 1. So 99.7% falls within 3% falls within 3 standard deviations of the mean. All right, so here's a distribution of heights of young women. We're going to reference to this problem over and over and over in this book. Aged 18 to 24 is approximately normal. Okay, so we're going to have this curve with mean of 64.5 inches and standard deviation of 2.5 inches. Okay, so this can be written like this, you guys. This n means normal. There's the mean, there's the standard deviation. Notice I put approximately normal in purple, so that means it's normal. The mean is in red and the standard deviation is in blue, so they're all color coded. So if you see approximately normal, then write it like this. So this is a shorthand. This means it's normal. That's the mean. That's the standard deviation. Okay, normal, mean, standard deviation. All right. So figure 2.12 on page 88 shows the 68, 95, 99.7 rule in this example. So let me show you what I'm talking about here. So right here, you guys, check it out. Let's see, did I do it on that side? I did. Okay, right there. Here's within one standard deviation of the mean. The mean, remember, the mean was 64.5. If I took, and the standard deviation was 2.5, you guys. So if I took off 2.5 that way, see, 64.5 minus 2.5 is 62. Okay, and then added 2.5 that way gets me 67. So if I go within one standard deviation to the left and to the right, that's 68% of the data. If I go 2 standard deviations, that's the next picture right here. There's 2 standard deviations. So minus 2.5 minus 2.5 gets me to 59.5. Okay, 64.5 plus 2.5 plus 2.5 is 2 standard deviations to the right and then 2 standard deviations to the left. That tells me that's 95% of the data falls between 59.5 inches and 69.5 inches. Okay, and that's what this says right here. 2 standard deviations fall from the mean mu is 10 inches. Okay. All right, because it's 2.5, 2.5 is 5, 2.5, 2.5 is 5 more, so 10-inch span right there. You guys with me? Yes. Okay, within 3 standard deviations. So I just went and subtracted 2.5 here, 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 got me down to 57, and then added 2.5 here, 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 and that got me up to 72. So between 57 inches and 72 inches is 99.7% of the data. All right. So here it is. So watch the slides. I'm going to go kind of fast. You don't have to write this down. You just watch. There's 68% of the data. There's 95% of the data. See, 2 standard deviations. There's 99.7% of the data. Okay, and remember the whole data is 100% or 1. Okay, so if we go 3 standard deviations to the left and 3 to the right, that gets me almost the entire curve, 99.7%. In fact, 0.3% is left, you guys. So 0.3% it would be from here and here. And since they're symmetrical, these would be equal. So this is actually 0.15%, which is 0.0015. And this is 0.15% also. Okay, we'll talk more about that in a little bit. All right, so check this out, you guys. If this is 68% of the data, that means there's 32% left to split up between these two tails because it's 100% for the whole curve. So if they're symmetrical, half of 32 is 16. This is the top 16% of the data. And if that's the top 16% of the data, then this must be my 84th percentile because my 100th percentile is down here or up here. And if I take off that 16%, that would get me to 84% right there. It's the 84th percentile. All right. Here's the so whoops, I don't have a line going right here. So oh no, now I do. Okay. So if this is 95% of the data right here, I should have another blue line right there. I wish I had time to do that. But from here down here to over here, that's 95% of the data. So that means this is 2.5%. This is 2.5%. That means this is the top 2.5%. This is the bottom 2.5%. What percentile is this right here? Yes, it's the 97.5 percentile. Over here, this is just the 2.5 percentile right there. Okay? All right, so that's what I said. And okay, so 3 standard deviations is from here to here. I have it right here, is 99.7%. Okay? Which means 0.30% is left with these 2 little tails right here. So this is 0.15. And if I take 0.15 off 100%, I get 99.85. This is the 99.85th percentile right there. Over here, this is the 0.15 percentile right there. All right, I don't think I have that. I don't. Okay, so what's the difference between the 80th percentile and the top 80%, if any? All right, the 80th percentile means that 80% of the data is equal to or below. The top 80%, which is what you guys are in, means you're in the top 80%. So your 80% of the data values are equal or above. You're in the top 80%, which means only 20% are above you, if at most. Explain the difference between the 80th percentile and the lower 80%, if there is any. There isn't. Okay, there is none. All right, if you're in my stats class, I would have you guys working on that homework assignment. Take care, you guys.